Bismillahirrahmanirrahim. Assalamu alaikum. So, it's our second lecture of this week, in which we have to discuss the applications of membrane. So, just to recall a few points from last lecture, yesterday I have talked about some general equation for membrane separation, and you have also discussed something related to mass transfer through membranes. As at the end of that lecture I have told you that we will discuss now various applications of membrane, and there are I think three main applications which we have to discuss or which are part of our syllabus. So, the first one, that's reverse osmosis. Let's start with this reverse osmosis. Actually, before this I was planning to go through gas separation and maybe power evaporation, but last lecture we discussed osmosis as well as osmotic pressure. So, this reverse osmosis very close to that topic. Due to this, I am going to discuss this topic in these two lectures. We will try to finish this reverse osmosis by end of this week, by next lecture. And this major stuff of this lecture is from your textbook. Maybe if small few points are from other sources, but overall if you want to go through textbook, that's enough. And I will advise you to go through textbook, because at the end of this reverse osmosis we have to solve a problem, and later you have to solve some unsolved problem related to that. So, it's better to go through or skim through the book, at least just check for few points. And also I will ask you during the lecture to go through some part of this text from your textbook. So, in this lecture, actually, our main series of lecture, I should say, this is not one lecture. Hopefully, we will cover this in two lectures. So, in these two lectures, we will study in detail related to reverse osmosis introduction and its mechanism, and then we have to see where it is applied, mainly its application and materials of which membranes are synthesized for reverse osmosis application, and the modules. You have already studied materials and modules, but specifically we will look which materials and modules are commonly used for reverse osmosis membranes. And then there is design, important parameters, where while you are designing a reverse osmosis system, with parameters you have to design or you have to calculate mainly. And at the end of that we have to solve a problem in which we will try to calculate few of those parameters. So, this is from last lecture. Just quick revision, that diffusion was actually solute movements from high concentration to low concentration, and we have talked about this in detail in last lecture. And while osmosis, that was movement of the solvent molecules. Opposite to this diffusion, it is movement of solvent molecules, and from where solvent molecules move, they move from low to high solute concentration. Anywhere where solute concentration is low, solvent will leave that part and it will move to the other side where there is high solute concentration. As you have seen here, that this is semi-permeable membrane, and it is partially it only allows solvent to pass through in any direction. Means solvent can pass, but solute particles are not allowed to pass through in membrane. And on the one side, left side, you can see that solute concentration is low, while on the right side its concentration is high. So, naturally osmosis phenomena takes place, and this liquid solvent will start traveling from left to the right, and with the passage of time, but you will observe the liquid level rises on the right side of the beaker, and it decreases or reduces on this left side, and it will continue till both sides reach to some equilibrium point. I have given one example of amount of salt and its concentration in last lecture, in which we discussed that when you reach to the equilibrium point, then this transfer stops, or maybe at that point even transfer is taking place, but transfer of liquid from left to right or right to left is equal. So, this system will be at equilibrium. There will be no change in the liquid level. This is also from the last lecture, in which we saw that if you have this like just YouTube, in which there is a membrane placed at the center, and on one side you have pure water while other side you have solution. So what do you think? Naturally the liquid will start flowing from this left arm towards right arm, and level inside right arm increases. And actually here we discussed that there is something called osmotic pressure, that's equal to like this change in the height, and you can calculate from this osmotic pressure. And if you want to keep the level of both sides liquid equal, what you have to apply? You have to apply some external pressure, and that will be equal to this osmotic pressure. When you apply external pressure equal to the osmotic pressure, then the liquid will be pushed from this side of the solution towards pure solvent, and it will like level will be equalized, which was disturbed due to movement of this pure water towards solution side. Now this was about osmosis, but our today's topic is reverse osmosis. So what we have to do here in this lecture, which we have to study, actually we have to move opposite to the osmosis. For example, just consider in this example, again you have here water on one side, or it contain very small amount of the solute particle, while on the other side there is concentrated solution which contain large amount of the salts. So through this semi-permeable membrane, which allows only water molecule or solvent molecule mainly to pass through, what will happen with the passage of time? This pure water solvent move towards solution side and level increases, as you have seen here. So now this is natural phenomenon, but if we have to push this back, mean this water or liquid which is pure solvent, if we want to push it back to the other side where it was pure or very small amount of salt were present in this system, so in that case you are applying some external pressure from here. So due to application of this external pressure, now what happened here? You see this external pressure which was applied equal to osmotic pressure. So the liquid moved from this seawater side or concentrated water solution side to the pure water side. So this phenomena is called reverse osmosis. Why we are calling it reverse osmosis? Because we are doing something reverse to the osmosis or opposite to the osmosis. In osmosis, actually when that's natural phenomena, and the liquid or water move from this side to the other side, but what we are doing here in reverse osmosis, actually we are moving water to the opposite side of a normal osmosis process, and this will be called as reverse osmosis. Like in reverse osmosis, one thing is clear from here or from the discussion before this, that you have to apply some external pressure. Now when you apply some external pressure, with the help of that external pressure, actually you are pushing the water through this semi-permeable membrane in the direction opposite to its natural flow or opposite to its natural direction of flow. So for example here you can see another example, like in reverse osmosis. Here this is one membrane which you can see like it is somehow membrane which is shown seems porous, but that is selective membrane. It only allows fresh water to pass through, and it didn't allow any salt or solute particle to pass through. So what's happening here? There is on this side, on right side, fresh water, and the other side there is salt water. So what do you think? Naturally what will happen? This fresh water actually will start traveling towards salt water, but we don't want it to pass through this, because this reverse osmosis is mainly applied for water treatment to get fresh water, clean water. So you have to purify it, you have to remove all impurities from that water. So for this purpose you have to apply some pressure. Now this pressure should be how much? We will look at this later in this lecture, but overall you can see from last slides to slide that this pressure is at least equal to that pressure is equal to osmotic pressure, so that this liquid can be moved from salt side to the fresh water side. When you are applying this pressure, so with the help of this you are actually pushing the water, and water will pass through this membrane while salts are retained. Here you can see these large molecules are of salt molecule which are rejected from the membrane. This is the phenomena of reverse osmosis, or how reverse osmosis takes place, that you have to apply some external pressure and that pressure is higher than the osmotic pressure, so then it will push water through the membrane in the direction opposite to its like natural flow direction. In your book, this description of osmosis, he has provided that this word osmosis actually came from the Greek word for push, mean push something, like you are in osmosis. What happens, this solvent is pushed through the semi-permeable membrane, or that travels from one side to other side, that is pushed through the membrane. So this osmosis came from that word push. Refer to the passage of the solvent such as water. This osmosis actually, you can just skip this part. So osmosis refer to the passage of solvent such as water through a membrane that is much more permeable to the solvent than to the solute. That solute can be inorganic oils, salts, anything like that. So that membrane is more permeable. Actually, as we are saying semi permeable, that is more permeable towards one stuff and one component, that is solvent here, and it is impermeable or maybe very slightly permeable to solute molecules. Overall, let's here we are going to consider one system in which there is one stage, and inside that stage, like there is one dense membrane in between that stage, and in the surrounding of that dense membrane, what you have, there is sea water of approximately 3.58% dissolved salts, and at 101.3 kilopascal in the cell 1. Like you have divided that, I will just show you in the next slide the diagram in which there is one stage of the membrane, and that stage is actually further divided into two cells or two parts. In between there is dense membrane, and in the surrounding or in the cell 1 there is sea water, and the other side there is pure water. So that membrane is actually permeable to water but not to the salts or salt present inside sea water. This membrane is semi permeable, that allows water mainly to pass through, and negligible amount of salt can pass through this membrane. So here is that system. For example, this is one stage in which you can see that there is a membrane. This is dense membrane placed inside this system, and there are two cells, cell 1 and cell 2. In cell 1 there is sea water, and other side there is a pure water, or maybe it will contain very small amount of salt. So what will happen, what do you think, when you just place this system or keep this system anywhere? Definitely this pure water will start traveling through this membrane, because membrane is permeable for water. It allows water to pass through, and it will travel to the sea water side. Why? Because due to osmosis phenomena, osmosis is natural phenomena in which solvent travels. If solvent can pass through this membrane, so definitely it will move towards the other side where there is high amount of salts, and salt water contain high amount of salt. He has told that this 3.5%. So with the passage of time, what will happen, water level will decrease on this side. Overall you can observe here, and it will increase on the other side, because water is traveled from cell 2 to the cell 1, and this phenomena is named as osmosis. But what you are looking for is opposite to this, in which you have to ask, or you have to just push the water in the opposite direction, as compared to this osmosis, in which what you have to do, you have to just push water from this cell 1 towards cell 2. So overall here you can see that this will have some pressure P1 due to hydrostatic head, static head pressure here due to this liquid head. Overall there will be some pressure, that's P is equal to rho g h. You can calculate this pressure. So overall initially let's consider pressure was equal, but initially pressure was equal, but due to transfer of this water from cell compartment 2 towards cell compartment 1 or cell 1, so level of the water rises on this side. Overall you can see, and due to this head of water, now pressure P1 will be higher as compared to pressure inside compartment 2, and this difference actually between P1 and P2 is equal to all this is somehow, most of the time it is equal to osmotic pressure, or this difference will be a bit less than osmotic pressure. if you have to move opposite to this, you have to go for reverse osmosis. So what you should have actually, this P1 minus P2 should be greater than the difference between our transmembrane pressure across the two sides of the membrane. That should be greater than osmotic pressure, then reverse osmosis will take place. So overall osmosis, if we look at this, osmosis is not a useful process. Why? Because in this we are not getting some separation, rather we are getting mixing. Overall, like here solvent is transferred in the wrong direction, the direction which we want to move the solvent, it didn't go to that direction, but it goes in the opposite direction. Solvent, water, pure water is moving towards the seawater, although in this application we are looking for pure water. So when water is moving from this pure water side to the seawater side, and which is the phenomena of osmosis, that's not desirable. That didn't provide you good solution, or I should say that provide, like, not provide separation, but it even provide mixing. So in order to avoid this, or in order to oppose this phenomena of osmosis, we have to increase the pressure, as I have told you in the last C part of the figure, that your pressure difference across the membrane P1 minus P2 should be greater than osmotic pressure, and in this case definitely reverse osmosis takes place and separation take place, your desired separation of this seawater into pure water, and retentate, that will be like somehow concentrated water or concentrated solution that's obtained. So for direction of transport of solvent through the membrane, that can be reversed by applying some pressure P1 that is higher than the sum of osmotic pressure and pressure P2. If you just rearrange this equation, what you will get actually, P1 will be equal greater than P2 plus pi. This pi is osmotic pressure, you know from the last lecture. So overall your pressure on this side should be higher. Now how you can increase this pressure? If you look at this diagram, here there is pressure due to the water head, but you know that due to water head, even this will reach somehow to the equilibrium, but it can't like move from this seawater side to the water side. Overall, in order to increase the pressure on this side, what you have to do, this is head pressure due to head, plus you have to apply external pressure, as we have seen in the last slide few diagrams. So when you will apply this external pressure, overall pressure on this side of the compartment, cell 1 will be higher, that will be totally P1, and then it will be higher than pi plus P2, osmotic pressure plus P2 pressure on the opposite side. So then this reverse osmosis phenomena and separation actually occurs. In this case, water from the seawater side is transferred to the pure water side, and seawater become more concentrated, because when some water, pure water will leave from there, so definitely the salt are left and some amount of solvent is left, so it becomes more concentrated, and this phenomena is named as reverse osmosis. Already you have seen from the figures. This reverse osmosis is used to partially remove solvent from the solute solvent mixture. Whenever you will have like solution, actually solute solvent mixture is called solution. So whenever you have solution and you want to separate those, so RO is used to partially remove the solvent, not totally 100%, like solvent is not removed in those system. Like you can't do this like all the solvent is removed and only salts are left on the other side. No, it didn't happen, and there is some reason behind that. You can't do this even. For that to move all the solvent to the other side, you will need very high pressure as well. When only salts are left, how you will remove the salt? They will be deposited on the surface of membrane. So due to these reasons, we remove only some part of the solvent from this solution, and other is concentrated is left. Here there is an important factor of osmotic pressure when you look at reverse osmosis. So important factor in developing RO separation processes is osmotic pressure, and osmotic pressure, yesterday you have seen that this is developed due to osmotic pressure is actually dependent on the solute concentration as well as the temperature. So for example, we discussed this last time also, that if you have pure water, so there is no solute, and pi was actually equal to molarity into R m molarity, that is actually number of moles over volume of solution. So into R into T. R is like gas constant that can be used, T is temperature, and m molarity. Now when there is no solute, definitely this term will be 0 and this osmotic pressure will be 0 as shown here. But most of the time when you are treating some water that contains salt that contain these impurities, so there will be some osmotic pressure, it will not be 0. And when it will not be 0, definitely it will play a role inside the separation, as we have seen that our pressure on the side of seawater or the side of wastewater which we are cleaning, so that should be equal to, pressure should be equal to P2 plus pi. So this pi osmotic pressure plays a role. If this is 0, definitely you will need less pressure on this side of P1. Sorry, it is greater, not equal. Actually it should be greater for reverse osmosis to take place. So if you just omit this, definitely only one factor is the pressure across the membrane, but if this is added, then this osmotic pressure is there. And it plays role in this separation. So here we can consider this RO membrane system for a liquid at high pressure containing solvent, for example water, and soluble inorganic salts that can be like NaCl, KCl, magnesium chloride, sodium chloride, and sometimes colloidal matter are also present in that. So that's the pressure side P1. Here look at this diagram. Actually here we have a membrane system, and on the one side your feed is entering, and that feed is the liquid feed, that's water containing some salts. This is feed side. On this side pressure is P1, and other side, that's permeate side, their pressure is P2, as you have seen in last section. So this water is not pure. Definitely we are looking for is cleaning, so it will contain some inorganic salt. There can be various impurities, but here just for example he is considered that inorganic salt like NaCl, KCl, MgClO2. There can be organic chemicals inside this. There can be colloidal that form somehow gel formation, like large chemicals are available, large molecules are present there. Then there are microorganisms inside that. So all these components are actually blocked by the membrane. Why they are blocked? Because your membrane here is overall that semi-permeable membrane, as he has shown here, that is asymmetric or thin film composite membrane. By the way, we will look at this why it is composite membrane or asymmetric, but before that this membrane is only permeable to the water. And by the way, one thing just remember from here, that it is not necessary that only water will pass. Somehow some salt can diffuse through this membrane, but they will be in very small amount. Their diffusion will be very less as compared to water. Due to this, mainly we just say that this is permeable for water, but you can't 100% retain all these components. Some of those can even diffuse through membrane and can go to the other side. On this side pressure P1, and for reverse osmosis to take place, you know that this P1 should be greater than P2, as he mentioned here, greater, it means it should be sufficiently higher than the P2 for reverse osmosis to take place, for this separation to take place. So overall here this membrane is actually asymmetric membrane. That's you remember asymmetric membranes are those membrane which are maybe formed of more than one component or more than one layers. I should say more than one layer. The top layer or the first layer, which is active layer, which is used for the separation, that's dense membrane. And here dense membrane such as acetate or aromatic polyamide, that's pump selective for the solvent. Only solvent can pass through, all other are retained on its surface. So this membrane, one layer will be the dense membrane, but you know that that's the one just layer, and that layer cannot sustain very high pressure. By the way, why we need here high pressure? As I told you that for more flux to get more pure water, you need high pressure difference here. And this high pressure difference some membrane, if it is just one layer, that cannot sustain that high pressure difference. It will rupture when you apply pressure is on its sides, both sides. So in order to avoid that rupture, what we have here, we built a membrane that's asymmetric. Asymmetric was a membrane which has top layer as the active layer, that was dense membrane, and below that there were porous membrane, microporous or microporous membrane, and they are not active layer. Actually they are just being used for the sport. We have discussed in last few lectures this phenomena. So just from there, that this composite membrane or asymmetric membrane is the same thing. That's composite, anything which is formed of more than one things, that's called composite. So here top layer is something dense membrane, and below that you have micro or macroporous membrane, and that is being used as a sport just to sustain high pressure. The products of reverse osmosis are retentate and permeate. So here the stuff which is leaving, which is pure water, that's permeate, and other which is solvent depleted feed. Solvent depleted means some of the solvent has been removed. Now depletion of the solvent has taken place because some of the solvent has left this feed, and that has become now part of permeate. So overall this solvent depleted feed is called retentate. So on this side, definitely at the end, if your feed was entering, when it will pass through this system, solvent will diffuse through membrane, it will move to the opposite side because here pressure is high and the other end pressure is low, so it moves due to this pressure difference. That's driving force actually. And then at the end of this membrane, here from here liquid retentate leaves. We just remove this liquid retentate, that's solvent deprived, or in which solvent is depleted feed. And why we do this? Actually we want to avoid the deposition of salts here in order to decrease the osmotic pressure, because when there will be more salts, there will be more osmotic pressure, and you will need then more pressure on this side for this liquid or solvent to pass through this membrane. So a perfect separation between solvent and solute is not achieved, since only a fraction of solvent is transferred to the permeate. Some amount of this is just transferred, all amount is not transferred. By the way, in your textbook he has discussed various applications here. I'm just going through them briefly, but later I will advise you to just go through the book. And he has mentioned that when you use membrane for some specific application, how much permeate actually you can recover, or how much solvent you can recover as a permeate. Suppose there was some specific amount of water, can we recover 100%? No, it will be less than 100%, but how much it can be, he has provided some specific example from industries. So just for your information, kindly go through them. So application of ROs, up to here one thing or more one things overall I have introduced you with the reverse osmosis system, that what reverse osmosis is. It is opposite to the osmosis. How it is opposite, we have seen this, and it is affected due to pressure, and we have seen that how much pressure should be there for something to pass through this membrane. Overall through this membrane all solvent is not recovered, some part is recovered. So next topic related to this reverse osmosis application. Reverse osmosis can be used for mainly water treatment. Now water treatment, there can be different type of water treatment depending on the feed. Like first feed, which is seawater, so this can be used, reverse osmosis can be used to desalinate and purify seawater. Actually seawater, how you define seawater, because later we will see there is something brackish water, there is some wastewater, so how you can differentiate them. So here I have provided definition for seawater. That's not from your textbook, it is from some other source. So seawater is the water in the words ocean. Definitely you will see, okay, this comes from ocean, this comes from sea, but not, this is not definition. Actually this water contain approximately 3.5% or 35 parts per thousand. This is 3.5%. Out of 100 100 parts, this is 3.5, but if you take 1000 parts, so there will be 35 parts of this. What does this mean? For example, if you take 1 liter of seawater, that will contain 35 gram salts. There will be 35 gram salts per 1 liter. 1 liter is equal to actually 1000 ml. So among 1000 ml of seawater which you collect, there will be 35 gram salt, and this is, by the way, world average. Later you will see that some of the sea, some sea around the world contain more salts, but some can contain somehow a bit less salts, but this is usually the seawater contain this much amount of salt. Overall, in this 1%, if you remember from Striker 1, that 1% is actually equal to 10,000 ppm. 10,000 ppm. So based on this you can say how much 3.5, it will be like 35,000 ppm, because 1% is this and he has mentioned 3.5, so it mean 3.5% mean overall it will be equal to, if you represent it in the form of ppm, so it will be like 35,000 ppm salt will be present in seawater. So actually mean reverse osmosis membrane are used on wide scale for this desalination. Desalination mean to remove salts, mean salt, salinate, desalinate. Salinate is to add salt, desalinate is to remove salt. So to remove salt and purify seawater we use this reverse osmosis membrane. This is one major and largest application of reverse osmosis. Then there is brackish water. Actually brackish water is the water which has we can say amount of these dissolved solid between seawater and fresh water, as he has mentioned that water with TDS, total dissolved solid. This is abbreviation of total dissolved solid from CPI lab, you remember hopefully this. So TDS, total dissolved solid content between that of fresh water. In fresh water actually we consider that the TDS is equal to or less than 500 milligram per liter, and in seawater as it is higher, like you can see from here he has mentioned like 33,000 to 48,000 milligram per liter, that's ppm, like 33,000 ppm to 48,000 ppm. This amount is present. So that's brackish water, that's also cleaned with the help of this reverse osmosis membrane. By the way, you can read about it, from where does it come. Most of the time in some areas actually it is formed or it come into existence when some water of sea is mixed with the fresh water, like of river water or rainwater in some areas, so that brackish water is formed. And then there is wastewater. So wastewater, any water that is contaminated by human activities, human use, for example industrial, domestic, agricultural, commercial, all those activities are considered under this wastewater. So all those industries, either textile industries, chemical industries, all various industries, leather industries, so which are contaminating the water leaving from those industries, that's actually contaminated, or that's those chemicals or various pollutants are added due to human activities. Due to this we call it like wastewater. The water leaving from home, domestic use, from kitchen, from wash basin, all that stuff is also domestic one. These are wastewater activities, like commercial activities, for example these car wash centers, so that can come under this category, and you can explore a lot of more. So reverse osmosis is also used for these systems, for cleaning of all this water also. So by the way, this wastewater will contain definitely dissolved solid less than both seawater and brackish water, but they will be still sufficiently high. This water will be not be fresh, that can't be used for drinking purpose, all other uses, so that need to be cleaned, and reverse osmosis is the best best way to treat this water. When you look at all these applications, so before 1980 actually only flash distillation, that is thermally driven process. Distillation, that needs a lot of heat, so due to this we are calling it thermally driven process. That was source of primary desalination processes before 1980. But from this 1980, last time also we discussed that a lot of membranes were developed in this era, and they were used for water treatment. So in 1990 first membrane was used for this reverse osmosis, and that was after that it became dominant process for cleaning of seawater. Actually, desalination is the terminology mainly used for cleaning of seawater. So before 1980, for cleaning of seawater only distillation was used. So how does distillation work? What you have to do, you have to separate the salts with the help of heating. You will evaporate the water. When water is evaporated, salt are left on the bottom of that unit in which this seawater was available. So then that water is condensed and separated, and pure water is obtained that can be used for various purposes. And this was definitely expensive as compared to this reverse osmosis, that's pressure driven process, and in this energy needed is less as compared to distillation. Due to this, it became more dominant. When you look at these reverse osmosis membrane, there were scientists, Loeb and his colleague, they developed an asymmetric membrane that allowed pressurized water actually to pass through at a high rate. When we started with the membrane separation, you have seen that membranes has he discussed there that initially membrane has many problem, and one of those was this problem, that to sustain at high pressure. Now suppose they took one membrane that was porous membrane. So you know porous membrane contain pore, and a lot of chemical, a lot of constituents of some sea water or other water can pass through that. But if you just synthesize the membrane in such a way that this membrane contain like porous membrane as a sport, and there is a top layer which is active layer, and that is dense membrane. So in this case, that dense membrane will only allow few components to pass through, and separation will be good. So when they developed this asymmetric membrane, that was a mixture of, as we have seen in last slide there, that was like dense membrane on the top, and then there was porous membranes below that to support. So those were first people who contributed towards this. Overall, when you look at this research, reverse osmosis data throughout the world till the publishing of this book, I think this book was published maybe I think in 2014 or 18, just confirm that. So till that there were 1,000 reverse osmosis plant. He has mentioned that when this book was published, there were almost 1,000 reverse osmosis plants which were operating in the world, and they were being used for mainly desalinating plants. Desalinating purpose, that means they were cleaning the seawater for various uses, and their production was on daily basis 750 million gallon per day. This is very huge amount. Just this is 750 and million, 750 million gallons per day of potable water that was like domestic use and other uses you can use it. So the largest plant, if you look at the data, largest plant in the world is located inside Israel. So that has capacity of I think almost this is 84.5 million gallons per day. So that is located on Mediterranean coast, and that supplies, book mentions that around 13% of the domestic water needed in Israel, this only one plant is providing. Also book mentions some plant in United States that's also provide some large amount of water. And similarly you can see, maybe we talked about this in the start of semester, that all these Gulf countries, they are mainly dependent on these reverse osmosis plants for their water needs, because they don't have any other freshwater resources like we have here. So they are using reverse osmosis plants, and throughout the world, like in Australia you can see, in Singapore there are many large plants which are located, and they are providing fresh water. So they all are using membranes actually. So up to here now you have idea about this, that they are reverse osmosis system are being used on large scale, and they are widely used in the world. So which material is used for developing or synthesizing the membrane which are used for these plants? So RO membrane for desalination, or so Here for desalination of water, to remove salts from sea water is accomplished mainly with if you look at modules, you have studied 4 different type of modules. So mainly spiral wound and hollow fiber membrane module are used for RO. If you remember, when we discussed those modules, there were 4 modules, and he has also told us at that time that spiral wound and hollow fiber are used for RO. So these are 2 major modules which are used. So the reason behind this was that they can be operated at high pressure, and also there were some other benefits. We talked about those, so you can go back and look at those. So these are 2 major modules which are used for reverse osmosis system. And when you look at the material of which membranes are constructed, our active layer actually is constructed at least. So they utilize cellulose triacetate, cellulose diacetate. They are actually based on cellulose, as well as there are some aromatic polyamide membrane material. So these cellulose acetate membrane and aromatic polyamide aromatic membrane, they can be used for this purpose, and they are these 2 or 3 types of membrane are widely used. So cellulose acetate are susceptible to biological attack. Suppose if you have cellulose membrane, so biological attack there are biological microorganism inside the water, so they can attack, or they can damage this membrane surface, as well as it gets destroyed due to acidic or basic hydrolysis. This cellulose triacetate or cellulose diacetate will react with, if acid or base is there, so it will go back to the cellulose. So when its structure is damaged, definitely it will not give you the separation which you were looking for. So due to this, it is necessary for the water which you are bringing, to make it necessary to chlorinate feed water. And with this chlorination, what happens actually, due to addition of this chlorine, microorganism like bacteria and fungus, these all are killed, and due to their killing actually you can avoid this attack. As well, to avoid this acidic or basic hydrolysis, you have to control the pH, and that should be between 4.5 to 7.5. So with the help of this, by chlorination, to kill these biological molecules, and to avoid this acidic and basic hydrolysis, you have to control the pH if you are using cellulose acetate membrane. On the other hand, you can use polyamide membrane, so they are not attacked by biological these microorganisms. If they are present in the water, various bacteria, algae, so they will not attack this kind of membrane if it is formed, active layer is formed of polyamides. But they resist hydrolysis in also, they are good, they resist hydrolysis in the pH range of 4 to 11. They, as compared to cellulose acetate membrane, you can see they can be used in wide range of pH, but they are attacked by chlorine. And by the way, this chlorine, it is usually already available in the water, because in sea water large amount of salts are there, and you know that chlorine will be there. Chlorine is dissolved inside the water, because these salt are just separated into their ions. So there will be sodium, for example, it was like sodium chloride, because sodium chloride is the largest or highest amount of salt which is present in the sea water. Mainly all others are present in less amount. This is a major contributor. Just check for this, that how much sodium chloride is present in the sea water as compared to other salts. I think this number should be greater than 80%. So in that case, when there will be sufficiently large amount of chlorine, if you are using cellulose acetate membrane, that chlorine is helpful for you, because it will kill biological microorganism, and it will be helpful for you. But if you are using polyamide membrane, now in this case definitely chlorine can cause problem. It is problematic to polyamide, that start reacting with polyamide and then damage this membrane structure. So in that case, we have to remove chlorine before bringing it to this stage of reverse osmosis. This is about material and modules which are commonly used now. At least you have idea that spiral wound and hollow fiber module are used, and cellulose acetate as well as polyamide membrane are used for this purpose. So when you look at this, feed water or sea water which is coming to RO units, so mainly we are discussing here sea water because major application of RO is for sea water, although it is also used now on domestic scale as well as for various industries, but major use from where it started, that was for sea water. So due to this, and the sea water, by the way, is the water which contain highest amount of the pollutants as compared to highest amount of these salts and all other pollutant as compared to any other water. So that's the main hardest case to clean. So due to this we are discussing that mainly everywhere, because if an RO membrane can clean seawater, it can be also easily used for cleaning of other water, brackish water or wastewater. So feed water to RO unit contain mainly potential foulants, which must be removed prior to the passage through membrane unit, otherwise performance and the life of membrane is reduced. What does this mean? Actually there are foulants. Foulants mean some chemical which start creating are which are deposited on the surface of membrane as a foulant. So due to this, it will happen due to this deposition. First of all, it will create one extra layer, and it will disturb the performance or passage of the solvent through the membrane, because this was membrane layer, only this resistance was there, but if fouling on the surface of membrane take place, another layer is formed, and that creates trouble in its performance. So in order to cross this resistance, definitely here you will need now more pressure on this side to pass this solvent from membrane as well. Due to these foulants, because they are depositing on the surface, so some of those start reacting with the membrane and reduce the life of membrane. Due to this, they should be removed, and we don't allow them actually even to come to this stage. We try to remove them before this water reach to membrane. Then there are suspended solid and particulate matter. So overall, here you will see the various example that there are various pollutants present in the water when you are bringing it to RO unit. So just for example, for 1 minute, just think that there is a membrane. This membrane is has such tendency that it will allow only water to pass through, and all other stuff will be retained on the surface of membrane, that will be rejected. But the problem is that all those pollutants are accumulated on the surface of membrane, and they will damage to the surface of membrane, they will reduce its life. So in order to avoid this problem, what we have to do, we have to remove them before bringing it to membrane. So now you will be thinking, okay, if you can remove anything before bringing it to membrane, so then what is the purpose of membrane? That's a good question. But actually some salts, we will look at next slide. So some salts cannot be removed unless you bring it to the reverse osmosis membrane. Some they call it like monatomic salts, for example NaCl. So that's difficult to remove with other filtration systems, so that can only be removed with the help of RO. But some other can be removed with other membrane microfiltration, ultrafiltration, maybe simple filtration system. So due to this, he has mentioned that these should be membrane in various, for example suspended solid. Suspended solid, they are just suspended. Particulate matter, that's particle, so they can be easily removed with the help of screening and filtration, ultrafiltration, microfiltration, nanofiltration, depending on the size of the suspended particle. So they can be removed before bringing it to the RO. Then there are colloids are flocculated and filtered. If there is something colloidal solution, something that's suspended, but like that cannot be just settled down due to gravity, or they cannot be separated just passing through the filter, because they are making like something colloidal solution. So in that case you add something called flocculants. And due to this, these are chemicals which are added. When they are added, they actually help these colloids to break, and those which were not settling naturally, now they can be settled because their colloidal solution, their forces are broken down and they can join each other. So just please go through this flocculation. What is flocculation? Just Google it if you are interested in more information. And when due to addition of these flocculants or extra chemical, then some of those chemical are separated, and you can easily filter them by using any of these membrane. And then there are scale forming salts. Scale forming, they form scale on the surface of membrane, they form a layer. Those salts required acidification or water softening or biological material require chlorine or ozonation. This should also be done because as you have seen that if you are using polyamide membrane, so then there is cellulose acetate membrane, so water should be chlorinated so that you can kill biological micromolecules, bacteria, algae, fungi that present in the water. As well, there is ozonation is needed. Ozonation mean addition of ozone, and ozone, you know that O3, and that will help you for oxidation of some of the chemicals. This can also be one of the treatment before you bring it to the reverse osmosis. And then water softening. Water softening is used for removal of, I think you know, the heavy water and its softening from FSC class. So that was removal of calcium and magnesium ions. So that can also be done before bringing it to RO, because that can be easily done in the softening units. You can use zeolite or other ion exchange stuff, and that is cleaned. Some organic foulants are removed by adsorption or oxidation. Some other which are not removed by this simple filtration, maybe by softening, ozonation, chlorination, so they can be used or removed with the help of adsorption. For example, adsorption on the surface of activated carbon. If you know activated carbon, that's carbon and that contain a lot of pores, so in those pores some of these impurities can be trapped. So for example, just look here in this diagram, you can get more clear idea that suppose you are using microfiltration. From last week lecture, hopefully you remember somehow or have idea of microfiltration. Pore were highest one, then the pore size reduced in ultrafiltration, and nanofiltration it was further reduced. In reverse osmosis we consider mainly that this is non-porous membrane. So in this microfiltration, just look here that water which contain various impurities. So water, there are monovalent ion, multivalent ion. Monovalent, like for example NaCl. Multivalent, like for example you have magnesium chloride, aluminum chloride, such chemical. Then there are viruses, bacteria, suspended solid. So overall you see that when you pass all this combination through microfiltration membrane, bacteria and suspended solids are separated. So in this we have removed some of those main stuff. Now if these four will jump towards next filter, that's ultrafiltration. So through this what you see that viruses can be easily separated. If you pass this water through the nanofiltration, you can see that most or major part of this multivalent ion is passed or removed. Some part will just pass through this membrane, major is just rejected here. So overall when it passed through this nanofiltration, you can see there will be water and monovalent ions. Now we have to separate actually water from monovalent ions, mean NaCl or KCl. So that's easy one, because if you apply reverse osmosis membrane through this membrane, now water can pass through and it will reject all other. If they were just reaching to this membrane, they will be separated, but most of them are usually separated before reaching to this stage. Only major monovalent ions are present. Why we are applying all these? Maybe you will be thinking, okay, if there is RO, why we are applying all these? We are applying all these to increase the life and sustainability of this reverse osmosis membrane. If we bring all these, definitely from this diagram you can see that they all can be rejected from here. This membrane will not allow any of those to pass through, but they will start depositing, they will start damaging this membrane. So due to this we remove them before bringing it to this. This is not only like micro, ultra and nanofiltration separation, that's pore size separation, but in last slide I have told you that you can use even adsorption, you can use oxidation, you can use ozonation. And in water treatment plants where or desalination plant where you are cleaning seawater, there are number of units which are installed before bringing this all to the reverse osmosis. So from this example also you can see here he has provided us various example of various stages of this membrane. He has shown just as in a form of like pipe through which this water is entering from this end, and when it is passing through, there is first microfiltration membrane, ultrafiltration, nanofiltration, and at the end reverse osmosis membrane. Before you reach to reverse osmosis, you can see here that more or less same things are removed, as like E. coli is bacteria, that is is removed here, some micromolecules are removed initially in this stage, microfiltration, then viruses and some protein are removed in next ultrafiltration. Small compound like magnesium chloride, calcium chloride, those are removed in this next nanofiltration, and only now NaCl and KCl are left along with water. So when you pass it through reverse osmosis, so in this only water will just pass through membrane, majorly water, very small amount of these salt will also pass through this membrane. So if we just don't remove all this stuff before bringing it to this membrane, so this membrane will be damaged and it will be ruptured easily, its overall performance will disturb. So due to this we apply all these stages and then bring this stuff to reverse osmosis. This is just let's look at this. This kind of equipment is also available in our department in environmental engineering lab. So there you can visit when you come back to the campus. Kindly go there and just observe this system. So in this system I will just explain you to the quickly, like here you have this is the feed pump, like it will be connected to some tank. Through this feed is enter, and here you can see these two large cylinder. What are these cylinder? Actually these are some filters. Sometimes we can have like simple mesh installed in this, simple screens which can retain these suspended solid, or one of this can be like sometime activated carbon, any other filter in which actually you remove some of those impurities before bringing it to the membrane. So after this you can see these filter, common filter which are used in the house for cleaning of water. So you remember, you know that they are simple filter based on size, as well as there is activated carbon filter. So some of those impurities will also be removed in this stuff. Actually from maybe it will not be too clear to you from here, but when you will visit the lab, environmental engineering lab, so there you can see easily all those pipings and that stuff. So after this, actually passing through this separation are these filter. Now the last stage is reverse osmosis membrane that is installed inside this module. So before just this liquid water enter to this module, there is a booster pump, high pressure pump that is installed. Why? Because we need high pressure across this membrane for this separation. So this salt water will enter to this booster pump, and then its pressure is increased, and then it will pass through the membrane and it gets separated into permeate and retentate, and then there will be some time post treatment, and that's it. So this is one lab scale equipment which is used as a reverse osmosis. This is one diagram from your textbook in which he shows that, for example, you have feed water that is coming from well or surface water, so you just pump to the RO plant. So this is first of all possible pre-treatment step, as I have told you or shown you here. Before bringing it to the RO, you just pass it through various other pre-treatment steps, or we have discussed like in these slides. So various that can be like filtration, coagulation, chemical injection, pH adjustment, chlorination, various other depending on your application. So after passing through this stage, now its pressure is again increased. Actually because this will be not only one stage, most of the time you have more than 2, 3, 4, 5 stages. So after passing water through these stages, pressure is further reduced. So in order to increase it to pass through reverse osmosis membrane, again one pump is installed. So this pump is high pressure pump. It will just increase its pressure, and this will pass through the RO membrane module. So after passing through RO membrane module, you can get from here permeate that has passed through this membrane, and we can go for further. For example, post treatment mean, for example, you have to add some of those solvent. Maybe sometimes you have to further go from some filtration, chlorination. That's not topic of this subject actually. Quickly, due to this I am going through this, but if someone is interested can ask me and I can answer those. For example, if there are still any bacteria or viruses here, post treatment can be like ultraviolet light. You can just throw that light and those will be killed, and you can get this water. Sometime if you have to distribute it for drinking purpose, because this membrane remove all major stuff, all salts, so we can make up salts. Usually these water supplying companies like Nestle or other, they are doing the same. They just pass water through the membranes and they remove each and every stuff, then they make up the salt required for our body. So all these are called post treatments. After this goes for distribution. From here membrane feed enters, permeate leaf from bottom, and there will be retentate. So retentate, because this was entered at high pressure, so that will contain sufficient energy, so that can be used for some energy devices. Actually there can be some turbine can be installed, or such system in which you can recover the energy. Most of the time there are turbines, so through that turbine you can recover some energy, and then this is discharged finally. So overall the idea here is that reverse osmosis plant or reverse osmosis system, when you look at this, that's not only membrane module, that contain other component, like there will be high pressure pump, there will be some pre-treatment unit, post-treatment units. So all this go your feed go through all these system, and then it is available for use. So up to here we have discussed in detail actually this membrane separation system. Next is RO membrane system design. By the way, I will just start next lecture from this point. So up to here I will just summarize what I have discussed today. We started with the introduction to reverse osmosis, but before that we just recall something from last lecture, some point that was osmosis, and then we said that reverse osmosis, opposite to the osmosis, I have discussed the phenomena, how does it work. Then after that we started with systems, how does it work in industrial scale. On industrial scale, what material are used, what modules are used, and on you have seen based on the data that they are used for various application. So that was like for seawater, for brackish water, for various wastewater treatments. So I will, as I advised during the lecture, again I am repeating that kindly go through your textbook. He has mentioned various wastewater treatment plants of various industries where reverse osmosis membrane are used. And then after that we have seen that how actually reverse osmosis system works. It is not only membrane module, but we have some other assemblies like post treatment, pre-treatments. Majorly pre-treatments are there actually to increase the life of this membrane and to make it more sustainable. So from here next lecture we will start, in which we have to look at some equation which are used for this designing of reverse osmosis membranes. Thank you so much. See you.